What if I told you that the peaceful, dark night sky you've looked at your entire life is actually a terrifying mathematical anomaly that defies the fundamental laws of classical geometry? Look up at the night sky. You perceive a vast, tranquil expanse of black, punctuated by the faint, scattered pinpricks of distant stars. It feels intuitive, peaceful, and entirely normal. But from a strictly mathematical and physical perspective, what you are looking at is a severe cosmological anomaly. By all classical laws of geometry, that sky should not be dark. It should be a blinding, continuous dome of radiation, glowing with the exact surface brightness of a star, vaporizing the Earth in an instant. This is not a philosophical musing. It is a rigorous quantitative contradiction known as Olbers Paradox. To understand why we are not currently being incinerated by the night sky, we must completely dismantle our intuitive understanding of time, space, and the biological hardware we use to perceive reality. Let us begin by establishing the mathematical severity of the problem. Assume for a moment the classical model of the universe, that it is infinite in extent, eternal in age, and relatively uniform in its distribution of stars. If you draw a line of sight outward from your eye in absolutely any direction, that line must, eventually, terminate on the surface of a star. Think of it like standing in the center of a vast, infinite forest. Even if the trees are spaced far apart, if the forest goes on forever, every single horizontal line of sight will eventually hit a tree trunk. There would be no gaps to see the horizon. In our theoretical infinite universe, the exact same geometric principle applies to stars. Now, you might argue that distant stars are incredibly faint due to the inverse square law of light, which states that brightness decreases with the square of the distance. This is mathematically true. However, the volume of space, and therefore the number of stars, increases with the exact same square of the distance. These two mathematical functions perfectly cancel each other out. A shell of space 10 times further away has stars that are 100 times dimmer, but that shell contains exactly 100 times more stars. Therefore, every single concentric shell of the universe contributes the exact same amount of ambient light to an observer on Earth. If the universe is infinite, there is an infinite number of shells. The integration of this light yields a sky of infinite brightness, capped only by the thermodynamic limit of the stellar surfaces themselves. The night sky should be a uniform, blazing inferno. Yet we measure a baseline optical darkness. The data directly contradicts the classical model. Somewhere in our fundamental assumptions about the architecture of reality, there is a catastrophic error. Before we can isolate the cosmic variables, we must first strip away the local illusions that corrupt our data, starting with the very atmosphere you are breathing. The human experience of a bright blue day and a pitch-black night is a highly localized planetary quirk, not a universal baseline. The daytime sky is not bright because the universe is bright. It is bright because of Rayleigh scattering. When solar photons hit the nitrogen and oxygen molecules in our atmosphere, shorter wavelengths, the blue end of the spectrum, are scattered highly efficiently, bouncing across the sky and hitting your retina from every conceivable angle. You are not seeing a bright sky. You are seeing a localized photonic pinball machine. If you were to instantly strip away the Earth's atmosphere, the daytime sky would immediately turn a terrifying, absolute black. The sun would appear as a blindingly harsh, defined disk, suspended in an abyss, exactly as it appears from the surface of the moon. On the moon, there is no atmospheric scattering reservoir. A shadow cast on the lunar regolith is a region of absolute, crushing darkness, devoid of ambient fill light. Conversely, on Venus, an atmosphere 90 times denser than Earth's scatters light so aggressively that the sun loses all definition, creating a uniform, sulfurous glow. The brightness of a planet's sky is merely a chemical atmospheric signature, totally irrelevant to the true optical baseline of the cosmos. By night, our atmosphere rotates away from the solar influx, the scattering ceases, and the gas becomes a transparent window. Only then are we actually looking at the universe. But even when we look through this window, human intuition is further corrupted by our own technology. We look at photographs taken by probes orbiting Saturn, or images of astronauts on the moon, and we see an inky black void completely devoid of stars. This visual data has led many to falsely conclude that space is simply empty. This is a profound misunderstanding of photoelectric engineering. A camera sensor, whether analog film or a digital CCD, is bound by dynamic range and exposure time. When imaging a highly reflective sunlit object like the rings of Saturn or a white EVA suit on the lunar surface, the camera shutter must operate at fractions of a second to prevent the sensor from saturating and blowing out the image. In that microsecond of exposure, the faint photons from distant background stars simply do not have enough time to accumulate in the sensor's pixel wells. They fall below the noise floor of the instrument. The stars are there, blazing in the background, but the camera is deliberately blinded to them to capture the foreground data. When we point space telescopes away from bright local objects and leave the shutter open for millions of seconds, the resulting data is staggering. The Hubble Ultra Deep Field proved that a patch of seemingly empty dark sky, the size of a pinhead held at arm's length, contains over 10,000 massive galaxies. The universe is not empty. It is densely, overwhelmingly populated. The geometric parameters of Olbers Paradox hold true. There is structure in almost every conceivable direction. So we return to the core contradiction. If the universe is packed with galaxies, why is it dark? Historically, astronomers attempted to salvage the eternal, infinite universe model by introducing auxiliary variables. The most prominent was the interstellar dust hypothesis. Scientists posited that vast clouds of opaque gas and dust between the stars were absorbing the light from distant galaxies, acting as a cosmic fog that shielded us from the infinite glare. It is an elegant hypothesis, but it fails the most basic laws of thermodynamics. Energy cannot be destroyed. If a cloud of interstellar dust continuously absorbs stellar photons, it will absorb that kinetic energy and begin to heat up. In an eternal universe, this dust would eventually reach thermal equilibrium, with the radiation hitting it. It would heat up until it glowed with the exact same surface brightness as the stars it was obscuring. The fog itself would become a blinding light source. The dark sky cannot be explained by obstruction. The resolution to this paradox requires us to abandon the classical universe entirely and embrace the framework of modern astrophysics. The dark sky is not an absence of light. It is a direct, visual measurement of the finite nature of time. The universe is not eternal. It has a highly specific age, calculated precisely at 13.8 billion years. This is the ultimate paradigm shift. Because the speed of light is a finite constant, approximately 300,000 kilometers per second, light acts as a cosmic clock. When we look at a galaxy 1 billion light-years away, we are not seeing it as it is today. We are analyzing photons that began their journey 1 billion years ago. Therefore, our vision is strictly bounded by a cosmological horizon. We can only see objects whose light has had less than 13.8 billion years to reach our detectors. What lies beyond that horizon? The geometry of space continues, likely filled with billions of other galaxies, but their light has literally not had enough time to cross the expanding void to hit our retinas. When you look into the darkest patches of the night sky, your line of sight is not terminating on empty space. It is terminating on the infancy of the universe itself, looking back to a temporal coordinate before the first stars had even ignited. The sky is dark primarily because the universe is simply too young to have filled it with light. But time is only the first half of the equation. The second half involves the fundamental geometry of space itself. We do not exist in a static void. According to Einstein's theory of general relativity, the metric of space is actively expanding. The vacuum between galaxy clusters is physically stretching, and this dynamic metric has a profound effect on the light traveling through it. Imagine a photon emitted by a distant galaxy, carrying a specific quantum of energy that corresponds to visible blue light. As this photon traverses the cosmos, the space it is traveling through expands. This expansion physically stretches the wavelength of the photon. By the time it reaches Earth billions of years later, its wavelength has been elongated, shifting its frequency down the electromagnetic spectrum. This is the cosmological redshift. Light that began its journey in the visible spectrum is stretched into the infrared, then into microwaves, and eventually into radio waves. This is the final, crushing blow to human intuition. The universe is actually blazing with radiation, but the metric expansion of space has stretched that radiation completely out of the narrow 400 to 700 nanometer optical window that human biology is equipped to detect. We are functionally blind to the true state of the cosmos. If you were to surgically alter your optic nerves to detect microwave radiation, the illusion of the dark night sky would instantly shatter. You would see a solid, uniform wall of blinding light in absolutely every direction, with no gaps, no shadows, and no darkness. This is the cosmic microwave background radiation, the literal afterglow of the Big Bang, emitted when the universe was a superheated plasma 380,000 years after its birth. It has been traveling for over 13 billion years, stretched by a factor of over 1,000 by the expansion of space, cooling from a blinding orange-white plasma to a frigid 2.7 degrees Kelvin above absolute zero. The sky is not dark. It is screaming with the residual thermal energy of creation, but you lack the biological hardware to process the signal. The optical darkness you perceive is merely a biological artifact, a limitation of primate evolution. But as we deploy our orbital sensors and map this invisible architecture, measuring the exact rate at which space is stretching, we have uncovered a variable in the data that is far more unsettling than the paradox we just solved. The expansion of the universe is not constant, it is accelerating, driven by a repulsive thermodynamic force we simply call dark energy. As dark energy accelerates this metric expansion, pushing galaxies beyond our cosmic event horizon, we are forced to confront a terrifying mathematical certainty about the ultimate fate of all matter. The metric expansion of space is governed by the Hubble parameter, but the introduction of dark energy, modeled quantitatively as the cosmological constant in Einstein's field equations, forces this parameter into an exponential acceleration phase. Because the recession velocity of any given cosmic structure is directly proportional to its proper distance from the observer, there exists a specific mathematical boundary, a spherical shell surrounding our local coordinate system, where the recession velocity formally exceeds the speed of light. This is the cosmic event horizon. Any photon emitted by a galaxy beyond this boundary today will never, under any mathematical model of our current cosmological paradigm, reach our detectors. The spatial metric between us and the source is being generated at a rate faster than the photon's propagation velocity. We are observing a universe that is systematically erasing its own observable history. Galaxies currently visible to our instruments are actively crossing this horizon. Their light will become increasingly redshifted, stretching into the radio spectrum until the wavelength approaches infinity and the signal amplitude drops to zero. The optical darkness of the night sky is merely a localized, temporary preview of a much deeper, permanent cosmological isolation. To fully appreciate the absolute necessity of this dynamic, expanding model, we must systematically dismantle the most intuitive, yet physically flawed, hypothesis historically proposed to explain the dark sky, the interstellar dust absorption model. Early astronomers postulated that the universe was infinite, static, and eternal, but that light from distant stars was absorbed by opaque interstellar particulate matter. Geometrically, this appears to resolve the paradox of a uniformly bright sky, but the hypothesis completely collapses when subjected to the fundamental laws of thermodynamics. Energy cannot be destroyed, it can only change state. When a silicate or carbonaceous dust grain absorbs an incoming photon from a distant star, the photon's kinetic energy is converted into thermal energy within the grain's crystalline lattice. According to the Stefan-Boltzmann law, any physical body with a temperature above absolute zero must radiate energy proportional to the fourth power of its thermodynamic temperature. As the interstellar dust clouds absorb continuous stellar radiation over an infinite timescale, their internal kinetic temperature must rise. They cannot absorb energy indefinitely without re-radiating it. Eventually, these dust grains would reach a state of perfect thermal equilibrium, where the rate of energy absorption precisely matches the rate of thermal emission. In a static, eternal universe uniformly populated with stars, this equilibrium temperature would inevitably equal the average photospheric temperature of the stars themselves. The dust would not obscure the light. It would become a brilliant, incandescent plasma glowing at thousands of degrees Kelvin. The entire sky, obscured by dust or not, would radiate as a perfect black body cavity, vaporizing any planetary body within it. The fact that the night sky is cold and optically dark is incontrovertible thermodynamic proof that the universe has not existed forever, and that it is not static. Another rigorous mathematical attempt to preserve the static universe model involved fractal geometry, specifically a hierarchical distribution of matter. Theorists proposed that stars are grouped into clusters, which are grouped into superclusters, separated by vast, exponentially scaling voids. If the density of matter decreases at a specific mathematical rate as the volume of observation increases, the integration of total starlight converges to a finite value rather than diverging to infinity. While mathematically elegant, this fractal model is aggressively contradicted by modern empirical data. Large-scale spectroscopic surveys, such as the Sloan Digital Sky Survey, have mapped the three-dimensional coordinates of millions of galaxies. The data conclusively demonstrates that beyond a scale of approximately 300 million light-years, the universe is highly isotropic and homogeneous. The distribution of matter ceases to be fractal and becomes a uniform cosmic web. Therefore, the finite integration of starlight cannot be attributed to a fractal spatial distribution. It is strictly bounded by the temporal limit of the universe's age and the metric stretching of space. Having established the physical parameters that dictate optical darkness, we must re-examine the sky through the extended electromagnetic spectrum, where the illusion of darkness is entirely dismantled. When we shift our sensor calibration from the 400 nanometer optical limit into the near and mid-infrared bands, wavelengths ranging from 1 to 25 micrometers, the structural architecture of the universe fundamentally changes. Infrared astronomy, spearheaded by cryogenic space observatories, bypasses the scattering effects of interstellar dust. Because infrared wavelengths are significantly larger than the average radius of cosmic dust grains, the photons undergo minimal Rayleigh scattering. They propagate cleanly through the dense molecular clouds that appear as pitch-black voids to human retinas. In these wavelengths, the dark patches of the Milky Way ignite with intense thermal activity. We detect the protostellar cores of nascent stars, still embedded within their accretion envelopes, radiating the immense heat of gravitational collapse. Furthermore, the infrared spectrum is the only channel through which we can observe the most distant, ancient structures in the universe. Because of the extreme cosmological redshift induced by metric expansion, the ultraviolet and visible emissions of the first generation of galaxies, formed a few 100 million years after the Big Bang, have been stretched by factors of 10 or more. A high-energy ultraviolet photon emitted at a redshift of z equals 10 will only be detectable by our instruments at a wavelength of approximately 1.3 micrometers, deep within the infrared. The optical darkness between the foreground stars is actually saturated with the ancient, red-shifted light of billions of primordial galaxies. They are not missing from the sky, they have simply been translated down the electromagnetic spectrum by the geometry of expanding space. If we invert our observational vector and push our sensors to the highest energy frequencies, the X-ray spectrum spanning wavelengths from 0.01 to 10 nanometers, we uncover a universe dominated by extreme gravitational and magnetic violence. The X-ray sky is not populated by stars, but by the superheated plasma trapped in the gravitational wells of galaxy clusters. This intracluster medium consists of ionized gas heated to temperatures exceeding tens of millions of degrees Kelvin. At these thermal extremes, the electrons are completely stripped from their atomic nuclei. As these free electrons are decelerated by the intense electromagnetic fields of nearby ions, they emit high-energy photons through a process known as thermal Bremsstrahlung, or breaking radiation. When viewed through orbital observatories, the supposedly empty voids between galaxies within a cluster glow with a blinding, diffuse X-ray luminescence. This plasma contains more baryonic mass than all the billions of stars within the cluster's galaxies combined. In addition to the diffuse Bremsstrahlung emission, the X-ray sky is punctuated by point sources of unimaginable luminosity, active galactic nuclei and quasars. At the center of nearly every massive galaxy lies a supermassive black hole, containing the mass of millions or billions of suns. When these singularities actively accrete surrounding matter, the infalling gas forms an accretion disk subject to extreme magnetorotational instability and viscous friction. The inner edge of this disk is heated to millions of degrees, radiating intensely in the X-ray band just before the matter crosses the event horizon. Furthermore, the complex interplay between the black hole's spin and intense magnetic fields often ejects highly collimated relativistic jets of plasma along the rotational axis. These jets pierce through the intergalactic medium at substantial fractions of the speed of light, generating massive shock waves that dominate the high-energy sky. The optical darkness is a biological blindfold, shielding us from the relentless thermonuclear and gravitational detonations occurring in every quadrant of the observable universe. Scaling up to the gamma-ray spectrum, the universe becomes highly transient and erratic. Gamma-ray astronomy reveals a sky that flashes and strobes unpredictably. These flashes, known as gamma-ray bursts, are the most luminous electromagnetic events occurring since the Big Bang. A typical burst can release more energy in 10 seconds than our Sun will emit over its entire 10 billion-year main sequence lifespan. These cataclysmic events are triggered by the core collapse of hypermassive stars into black holes, or the violent orbital decay and merger of binary neutron star systems. For a brief moment, a single burst outshines the rest of the gamma-ray universe combined. If human eyes were sensitive to gamma radiation, the night sky would resemble a chaotic, high-energy strobe light, with blinding flashes randomly illuminating the celestial sphere from billions of light-years away. Dropping to the lowest energy regime, the radio spectrum, we map the universe through wavelengths measured in centimeters and meters. Here, emission shifts away from thermal processes. The radio sky is heavily populated by synchrotron radiation, generated when relativistic electrons spiral along intense magnetic field lines. Pulsars, rapidly rotating neutron stars with magnetic fields trillions of times stronger than Earth's, sweep beams of coherent radio emission across our line of sight. Additionally, radio telescopes utilizing highly sensitive interferometry map the 21-centimeter emission line of neutral hydrogen. This specific frequency is emitted when the electron in a hydrogen atom undergoes a spin-flip transition. By mapping this 21-centimeter signal, astronomers can trace the immense, invisible filaments of cold hydrogen gas that stretch across the intergalactic voids, forming the foundational scaffolding of the cosmic web upon which all galaxies are built. Yet, even the complete electromagnetic spectrum, from radio waves to gamma rays, only represents a fraction of the data streaming through the cosmos. The universe is actively communicating through non-electromagnetic channels, requiring an entirely new paradigm of observational infrastructure, multi-messenger astronomy. Consider the neutrino, an elementary particle with a mass so infinitesimally small it has yet to be definitively measured, and which interacts with ordinary matter only via the weak nuclear force. Trillions of cosmic neutrinos pass through every square centimeter of your body each second, generated in the nuclear furnaces of stellar cores, the shock waves of supernovae, and the accretion disks of supermassive black holes. Because they possess no electric charge and interact so rarely, neutrinos travel in perfectly straight lines across billions of light-years, passing unimpeded through dust clouds, planets, and stars. To detect them, we have constructed massive observatories like IceCube, burying thousands of photomultiplier tubes deep within the pristine glacial ice of Antarctica, waiting for the microscopic flash of Cherenkov radiation emitted when a neutrino occasionally collides with an atomic nucleus. The final and perhaps most profound channel of cosmic data bypasses particles and radiation entirely, manifesting as literal distortions in the metric of space-time itself. Predicted by general relativity, gravitational waves are ripples in the space-time fabric generated by the asymmetric acceleration of massive objects. When two orbiting black holes spiral inward and merge, they convert a percentage of their combined mass into pure gravitational energy in a fraction of a second, sending a shockwave of stretching and squeezing space-time outward at the speed of light. We detect these waves using kilometer-scale laser interferometers, measuring spatial distortions significantly smaller than the diameter of a single proton. When we observe the universe through gravitational waves, the optical darkness is entirely irrelevant, because we are no longer relying on the propagation of light to map the cosmos, but rather feeling the geometric vibrations of its most violent mechanical collisions. The true power of modern astrophysics lies in the synthesis of these disparate data streams, formally classified as multi-messenger astronomy. When two neutron stars collide, the event is not isolated to a single frequency. It initiates a gravitational wave transient that distorts the local metric of space-time, followed milliseconds later by a highly collimated short-duration gamma-ray burst. As the ejected neutron-rich material undergoes rapid neutron capture nucleosynthesis, it produces a kilonova radiating across ultraviolet, optical, and infrared wavelengths. Over subsequent months, as the decelerating ejecta interacts with the interstellar medium, it generates an afterglow detectable in X-ray and radio frequencies. The optical light, the singular band to which human biology is naturally sensitive, constitutes merely a fractional component of a vastly more complex energetic transfer. The dark optical sky must therefore be contextualized as an observational artifact resulting from our biological constraints, representing an infinitely narrow slice of a multi-channel cosmic broadcast. To comprehend the universe in its totality, we must acknowledge that the optical darkness is a highly specific, relative deficit of radiation. Biologically, the human retina is optimized for the peak emission spectrum of a G-type main-sequence star, constrained to detect electromagnetic radiation roughly between 400 and 700 nanometers. This narrow bandwidth is an evolutionary adaptation to the atmospheric transmission window of Earth, maximizing visual acuity in the environment where our species evolved. It is not an objective metric of cosmic luminosity. If our sensory apparatus were calibrated to microwave frequencies, the night sky would exhibit an unbroken, isotropic luminance from the cosmic microwave background, glowing uniformly at 2.7 Kelvin. If our visual cortex processed high-energy X-ray photons, the sky would be brilliantly punctuated by the accretion disks of supermassive black holes and the superheated intracluster medium-permeating galaxy clusters. Every subsequent generation of astronomical instrumentation, from the earliest parabolic radio antennas to the cryogenically cooled mirrors of the James Webb Space Telescope, has effectively widened our sensory bandwidth. Each technological leap has revealed entire populations of celestial sources, previously masked by the optical darkness. Infrared observatories penetrate dense molecular clouds, revealing the thermal signatures of protostars and the redshifted light of the most distant galaxies. Gamma-ray detectors map the violent decay of exotic particles and the explosive deaths of massive stars. The universe does not restrict its energetic output to the wavelengths we find convenient. It broadcasts continuously across the entire electromagnetic spectrum. The darkness between the stars is, in part, a precise measurement of how narrow our biological eyes truly are. Despite the inherent limitations of our biological optical sensors, the visible darkness overhead remains a profound repository of cosmological data. It is a rigorous scientific measurement, accessible without specialized instrumentation, yielding fundamental parameters regarding the origin and evolution of the universe. To fully integrate the resolution of the dark sky paradox, we must synthesize the multiple physical mechanisms that collectively engineer the optical darkness we observe. This requires gathering the theoretical and observational threads we have examined and laying them out with academic precision. The dark sky is the emergent property of 7 distinct physical and biological factors operating in tandem. The first thread is local and atmospheric. The terrestrial daytime sky appears brilliantly illuminated solely due to Rayleigh scattering, wherein atmospheric gas molecules elastically scatter incident solar photons, redistributing the direct beam across the celestial dome. In the absence of this atmospheric diffusion, as empirically verified by astronauts on the lunar surface, the sky remains an absolute, featureless black, irrespective of direct solar illumination. The bright daytime sky is a localized meteorological optical illusion, not a property of the surrounding universe. The second thread is photographic and mechanical. The apparent absence of a stellar background in astrophotography is a strict mechanical constraint of sensor exposure latitude, not a reflection of cosmic sparsity. Capturing high albedo foreground targets necessitates extremely short integration times to prevent sensor saturation. Consequently, the faint stellar background remains entirely undetected beneath the sensor's noise floor. When cameras are configured with extended integration times, the resulting deep-field images reveal a universe densely populated with galaxies in every conceivable direction. The third thread is cosmological and geometric. The original formulation of the paradox correctly deduced that an infinite, eternal, and static stellar distribution must mathematically yield an infinitely bright sky. The volume of distant spherical shells increases at the exact rate necessary to offset the inverse square diminution of individual stellar fluxes. The stark divergence between this mathematical prediction and our empirical observation of a dark sky strictly falsifies the underlying cosmological premises of classical natural philosophy. The fourth thread is temporal. The universe possesses a strictly finite temporal duration, currently calculated with high precision at 13.8 billion years. Consequently, our observable volume is bounded by a light travel time horizon. Lines of sight extending beyond this boundary do not intersect stellar photospheres. They intersect the primordial epoch of the universe preceding the formation of the first stars. The simple geometric integration fails because it erroneously assumes contributions from arbitrarily distant sources whose light has not had sufficient time to traverse the intervening space. The fifth thread is spatial and metric. The universe is not a static grid. The metric of space itself is undergoing continuous expansion. As photons propagate across cosmic distances, this expansion dynamically stretches their wavelengths. This cosmological redshift systematically shifts the emission spectra of distant galaxies out of the visible band and into the infrared and microwave regimes. Therefore, even the light that has had sufficient time to reach us is actively shifted beyond our biological detection threshold, darkening the optical sky as a strictly increasing function of distance. The sixth thread is dynamic and accelerative. The expansion of the universe is accelerating, driven by the vacuum energy density categorized as dark energy. This acceleration establishes a cosmic event horizon, a strict boundary beyond which emitted light can never overcome the expanding metric to reach our coordinates. There are galaxies currently receding from us at superluminal velocities, rendering their future emissions permanently inaccessible. The dark sky, therefore, contains vectors of absolute, permanent optical silence. The seventh and final thread is biological. As established, the optical darkness of the night sky is a direct feature of our physiological constraints. We observe the cosmos through a highly restrictive biological filter, sensitive only to a minute fraction of the total electromagnetic spectrum. The universe is ablaze with radiation, but our evolutionary biology restricts our perception to a localized optical sliver. These 7 threads, atmospheric geometry, sensor dynamic range limitations, the failure of the infinite static model, the finite age of the cosmos, The metric expansion of space, the acceleration driven by dark energy, and the narrowness of our biological window weave together to produce the exact sky we observe. The dark night sky is the mathematically predictable output of a young, expanding, and highly structured universe. It is a satisfying and elegant resolution, devoid of ad hoc variables or contrived thermodynamic patches. The historical trajectory of this paradox perfectly illustrates a fundamental pattern in the advancement of scientific thought. For centuries, natural philosophers attempted to resolve the dark sky by appending minor adjustments to an incorrect cosmological model, proposing intervening dust clouds or fractal stellar distributions. Yet, thermodynamic equilibrium dictated that intervening dust would eventually radiate with the intensity of a stellar surface. The puzzle remained intractable until the foundational paradigm itself was overthrown. Once the static, eternal universe was replaced by the dynamic, finite-aged model of modern general relativity, the paradox did not merely find a solution. It dissolved entirely. The dark sky transitioned from being a contradictory anomaly to serving as foundational evidence for the Big Bang and cosmic expansion. There is a profound elegance in recognizing that the gaps between the stars are just as informative as the stars themselves. The darkness is an honest representation of our cosmological reality, a signature written in absence rather than presence. It allows us to comprehend the scale, age, and dynamic nature of the universe simply by observing what is not there. We do not need to physically travel to the cosmic event horizon to verify its existence. It manifests as the impenetrable blackness at the edge of our deepest observations. We do not need to isolate a single photon to prove space is expanding. The expansion reveals itself by shifting the universe's background radiation into the invisible microwave spectrum, leaving the optical sky dark. As we continue to decode these cosmic signatures and push the boundaries of multi-messenger astronomy, your engagement through subscribing to the channel, leaving a comment, or liking this transmission directly supports the ongoing expansion of our scientific dialogue. It allows us to delve deeper into the mechanics of the universe, translating complex astrophysical data into accessible, rigorous narratives. Your participation is a vital component of this educational endeavor. The night sky overhead is a quiet, continuous lecture on the mechanics of space-time. It demands no specialized instrumentation to appreciate, only the patience to look upward and the curiosity to question the absence of light. When you next stand beneath a clear, dark sky, observe the familiar constellations, but direct your attention equally to the vast, dark expanses between them. That blackness is not an empty void. It is a dense repository of cosmic history. It is filled with the red-shifted light of primeval galaxies, the relic radiation of the Big Bang, the geometric ripples of colliding black holes, and the silent trajectories of 1 trillion neutrinos. It is the universe, young and expanding, viewed from the inside out. Let the profound scale of this reality settle into your mind. Let your breathing slow. Let the analytical demands of the day fade away. Sleep well, and good night.